Hello, and welcome. Tonight, we're going to follow a single grain of sand on its journey. Not a rushed journey, not an exciting adventure, but a slow, patient transformation that takes place over thousands, sometimes millions of years. Take a moment to settle in. Get comfortable. There is nowhere you need to be, nothing you need to remember. This is simply a story about patience, about the slow work of water and wind and time. If you drift off before we finish, that is perfectly fine. The sand will continue its journey whether we're watching or not. That is one of the comforting things about geology. It happens whether we observe it or not, in its own time, at its own pace. Let's begin at the very beginning, before our grain of sand was sand at all. Our story starts in a mountain, not any particular mountain really. This could be the Rockies, or the Himalayas, or the Appalachians. The specifics don't matter so much. What matters is that there is a large mass of rock, high above sea level, exposed to the air and the weather. The rock we were interested in is granite. Granite is an igneous rock, which means it formed from molten magma, deep beneath the Earth's surface, cooling very slowly over thousands of years. This slow cooling is what gives granite its characteristic appearance. You can see individual crystals of different minerals when you look closely at a piece of granite. Quartz, feldspar, mica, each one formed as the magma cooled, molecule by molecule, arranging themselves into orderly crystal structures. The particular crystal we're following is quartz. Quartz is silicon dioxide, one atom of silicon bonded to two atoms of oxygen, repeated in a three-dimensional lattice that extends in all directions. It is quite a strong bond, chemically speaking. Quartz is hard, resistant to most acids, and doesn't weather easily compared to many other minerals. But nothing lasts forever, of course, not even quartz. Our quartz crystal, right now, is locked deep inside a mountain, surrounded by feldspar and mica and other minerals. It has been there for perhaps 50 million years. Humans haven't evolved yet. Dinosaurs came and went millions of years before this mountain even began to form. The mountain is slowly rising. Not quickly, perhaps a few millimeters per year. This is happening because of tectonic forces deep beneath the Earth's crust, where two continental plates are very gradually pushing against each other. The rock has nowhere to go but up. As the mountain rises, the rock that was once deep underground becomes exposed to the surface. The pressure changes. Most importantly, the rock meets water and air for the first time in millions of years. Water begins to seep into tiny cracks in the granite. During the day, when the sun warms the mountain, the water is liquid. At night, especially in winter, the water freezes. When water freezes, it expands not dramatically, but noticeably. About 9% more volume as ice than as liquid water. This expansion creates pressure. Tiny cracks become slightly larger cracks. Over thousands of thaw cycles, the cracks grow. It is an incredibly slow process. A crack might widen by a fraction of a millimeter per year, but over 10,000 years, over 100,000 years, it adds up. Eventually, and this might take 100,000 years or more, a piece of granite breaks free from the mountain face. Perhaps it is no larger than your fist, this chunk of granite. It tumbles down the mountainside, bouncing off other rocks, breaking into smaller pieces as it falls. Our quartz crystal is still embedded in a piece of granite, but that piece is now much smaller, maybe the size of a walnut. It comes to rest in a rocky crevice, alongside thousands of other rock fragments that have made similar journeys down the mountain. Here, the next phase of weathering begins, chemical weathering this time. The feldspar minerals that surround our quartz crystal are less stable than quartz when exposed to water and air. Feldspar contains aluminum, potassium, and sodium, among other elements, and water can slowly react with these minerals, dissolving some components and transforming the feldspar into clay. This clay is soft, crumbly. As the feldspar turns to clay, the granite fragment begins to fall apart. The individual mineral grains that were once locked together start to separate. One day, though day is perhaps not the right word for a process that takes thousands of years, our quartz crystal finally separates from its neighbouring minerals. It is no longer part of granite. It is a single crystal of quartz, irregular in shape, perhaps 3 millimeters across at its widest point. still quite angular, with sharp edges where it broke away from the surrounding rock. This is not yet sand, not quite. Sand is defined by size. Particles between about 0.0625 millimeters and 2 millimeters in diameter. Our quartz grain is at the larger end of sand size, what geologists call coarse sand. But more importantly, sand tends to be rounded, smoothed by abrasion. Our quartz grain is still angular, fresh from the granite. It needs to travel further, to tumble and roll and gradually wear down those sharp edges. That journey is about to begin. The mountainside where our quartz grain now rests is steep, but not steep enough for the grain to simply roll down on its own. Quartz is denser than water, about 2.65 times as dense, so it won't float away. It needs moving water to transport it. Rain comes to the mountain regularly. Most of the time, the rain soaks into the soil or evaporates back into the air. But sometimes, during heavy rainstorms or during spring snowmelt, there is more water than the soil can absorb. This excess water runs down the mountainside in small streams. These streams are temporary, existing only during and shortly after rain events, but they are powerful enough to move small rocks and mineral grains. Our quartz grain waits, settled in its crevice, as hundreds of small storms pass over the mountain. The water flows around it, but doesn't quite generate enough force to dislodge it. Then, one spring, an unusually heavy snowpack begins to melt. Perhaps the winter was particularly snowy, or perhaps spring came early and warm. The exact reason doesn't matter. What matters is that an exceptional amount of water is flowing down the mountain. The temporary stream becomes a torrent. Water rushes past our quartz grain with enough velocity to pick it up and carry it along. The grain tumbles in the current, bouncing along the rocky stream, colliding with other pebbles and grains. Each collision knocks off a tiny fragment. The angular edges begin, very slowly, to round. The stream carries the grain downhill for perhaps 50 meters before the water slows and the grain settles again. This pattern repeats over years and decades. A storm comes, the grain moves a little farther down the mountain, then settles again. And we were talking about a process that might take 1,000 years or more. The small, temporary stream joins a larger, more permanent stream, and this larger stream, fed by snowmelt throughout most of the year, eventually flows into a river. Rivers are different from mountain streams. They flow constantly, or nearly so. They have enough volume to move even large rocks during flood events, and they are constantly moving sand and silt and clay. Our quartz grain enters the river during a spring flood. The water is brown with suspended sediment, carrying clay and silt from upstream. The grain bounces along the riverbed, sometimes rolling smoothly, sometimes making small hops when the current is particularly strong. The river is much gentler than the mountain stream in one way. The impacts are less violent, because the grain is now surrounded by water and other sediments that cushion the collisions. But the river moves the grain much farther, much more consistently. Every time the grain bounces or rolls along the riverbed, it knocks against other grains of quartz, fragments of other minerals, smooth river pebbles. Each contact wears away a microscopic amount of material. The sharp edges continue to round. The grain becomes smoother. The river meanders back and forth across its valley. Sometimes, during floods, the river overflows its banks and deposits sediment on the floodplain. Our quartz grain might be deposited in the floodplain and spend a few decades there, buried under other sediments, waiting for the river to erode its bank during another flood and pick up the grain again. This is not a straight journey. The grain might move 100 meters downstream during one flood, then get deposited in a quiet backwater and sit there for 50 years before moving again. Rivers are patient. They have no schedules to keep. Over centuries, the grain gradually works its way downstream. The river leaves the mountains and enters foothills, then a broad valley. The current slows. The grain spends more time resting on the riverbed, less time in motion. By now, the grain has been tumbling and rolling for perhaps 10,000 years. It is noticeably smaller than it was when it first broke free from the granite, perhaps 2 millimeters across now instead of 3. The sharp, angular edges are completely gone. If you could hold it in your hand and look at it through a magnifying glass, you would see a rounded, smooth grain of quartz, translucent or milky white, with tiny pits and scratches on its surface from its countless collisions. This is now unambiguously sand. It looks like what you find on a beach or in a sandbox, but it hasn't reached a beach yet. It is still hundreds of kilometers from the ocean. The river carries the grain farther downstream, through farmland and forests. The river is quite slow here, broad and meandering. During normal flow, the grain sits on the riverbed, barely moving. Only during floods does it get picked up and carried along. The grain might spend 1,000 years travelling this final section of the river, moving intermittently, slowly making its way toward the sea. And then, finally, the river widens. The water becomes brackish, a mix of fresh river water and salty ocean water. Tides push back against the river's current twice a day. The river has reached its delta, the place where it meets the ocean. River deltas are dynamic places, constantly changing. The river deposits sediment here, sand and silt and clay carried from far upstream. Over time, this sediment builds up, forming new land. The river branches into multiple channels called distributaries that spread out across the delta like fingers. Our quartz grain is deposited in one of these distributary channels during a flood. It settles into the sediment, surrounded by other sand grains, some of quartz like itself, others of feldspar or fragments of rock. The sediment here is layered. New layers are added with each flood. Our grain becomes buried under fresh sediment, cut off from the light, pressed down by the weight of the material above it. It might stay here for a very long time. Some sediments in river deltas remain buried for millions of years, slowly compressing and cementing into sedimentary rock. But our grain's journey isn't over yet. The delta is not a stable environment. Rivers change course. A flood might cause a distributary channel to shift, eroding the bank where our grain is buried and exposing it once again to flowing water. Or ocean waves might erode the delta front during a storm, washing the sediments, including our grain, out into deeper water. In this case, a storm does the work, a hurricane perhaps, or just a particularly strong winter storm that generates large waves. These waves crash against the delta, stirring up the sediment, and carry it out into the ocean. Our quartz grain, which had been buried and resting for perhaps a few hundred years, is now suspended in ocean water, carried by currents parallel to the shore. These coastal currents are called longshore currents. They're created by waves approaching the shore at an angle. The water and sediment move along the coast in one direction, parallel to the beach. It is these currents that transport sand along coastlines, sometimes building up sand in one area while eroding it from another. The grain travels along the coast in this current for some distance, perhaps dozens of kilometers, before the current weakens and the grain settles again. This time, it settles on a beach. The beach is quite different from the river or the delta. Here, the grain is exposed to air part of the time. Waves wash up the beach face, then recede. Twice a day, the tide comes in and goes out. The grain is moved up and down the beach by the waves, tumbling in the swash zone, where waves break and foam rushes up the sand. This constant tumbling in the surf zone rounds the grain even more. The impacts are different here. Collisions with thousands of other sand grains in the turbulent water, right at the beach face. The grain becomes more spherical, more polished. Beaches are not permanent either. A storm might strip away the sand, carrying it offshore to form underwater bars. A period of calm weather might allow the sand to accumulate again. Our grain moves on and off the beach multiple times over the years. Sometimes the grain is blown inland by the wind. Beaches are windy places, and dry sand is light enough to be moved by wind. The grain might be carried into coastal dunes where it settles among other sand grains, held in place by sparse beach grass. Dunes are relatively stable environments, at least compared to the active beach. The grain might rest in a dune for decades or even centuries, slowly buried as the dune grows. But dunes also migrate over time, as wind erodes sand from the windward side and deposits it on the leeward side. The dune slowly walks across the landscape. Eventually a storm erodes the dune, or the dune reaches the beach again, and our grain is once more in the ocean. Not all sand stays on the beach. Some of it is carried farther offshore into deeper water. This happens most commonly during large storms, when powerful waves and currents can transport sand to depths where normal wave action doesn't reach. Our quartz grain, during a particularly violent storm, is carried offshore and settles on the ocean floor in about 20 meters of water. The water here is relatively calm, below the depth where most wave action disturbs the bottom. The grain settles into the sediment, surrounded by other sand grains, bits of shell, and the remains of microscopic marine organisms. The ocean floor at this depth is not lifeless. Small fish swim by occasionally, crabs walk across the bottom, worms burrow through the sediment, but mostly it is quiet. The light that filters down from above is dim, greenish, blue. Our grain rests here for a long time, centuries pass. More sediment slowly accumulates on top of it, a few millimeters per year, perhaps. The grain is gradually buried deeper in the sediment. As the sediment accumulates, the pressure on the grain increases. The weight of the overlying sediment presses down. In some environments, this pressure, combined with minerals dissolved in seawater that percolate through the sediment, can cement the sand grains together into sandstone. But our grain doesn't become part of a rock. The conditions here aren't quite right for cementation to occur extensively. The sediment remains loose, unconsolidated. Deep in the sediment, it is dark. There is no light at all. The grain is surrounded by other mineral grains and organic matter that is slowly decomposing. Bacteria in the sediment break down organic material, using up any oxygen that might have been present. The environment becomes anoxic without oxygen. Time passes very slowly here. Nothing much happens. The grain doesn't move, it doesn't erode, it simply exists pressed between other grains, in the dark, in the quiet. Thousands of years go by this way. 10,000 years, 20,000. The grain has been on its journey for hundreds of thousands of years by now, from mountain to river to delta to beach to ocean floor. If the grain could experience time, this period on the ocean floor might feel like an eternity. But even the ocean floor changes, though very slowly. Sea levels rise and fall over geological time, responding to ice ages and warming periods. When ice sheets grow on land during ice ages, they lock up water from the oceans, and sea levels drop. When ice sheets melt, sea levels rise. During one of these changes in sea level, perhaps it takes 10,000 years for the change to complete. The ocean above our grain becomes shallower. The water that was once 20 meters deep is now only 10 meters deep. This brings the grain back into the zone where waves can occasionally stir up the bottom sediment during storms. A powerful storm passes over. The waves reach down and disturb the sediment. Our grain, after 20,000 years of quiet rest, is picked up by the turbulent water and moved. It doesn't go far, just a few meters before settling again. But it is now in slightly shallower water, where waves disturb the bottom more frequently. Over the next few centuries, the grain is moved repeatedly, gradually working its way back toward shore. Eventually, the grain returns to the beach. It has been gone for perhaps 25,000 years. If there were humans on this beach before, and there might have been 25,000 years ago, they're long gone now. Their civilizations rose and fell while the grain rested on the ocean floor. But the grain is unchanged, essentially. Perhaps a tiny bit smaller from the abrasion during its time in the surf zone before it went offshore, and from the recent tumbling as it returned to shore. But quartz is durable. The grain is still recognizably the same grain that broke free from a mountain. Perhaps 200,000 years ago, it settles onto the beach, just one grain among billions, indistinguishable from the others. There is something meditative about this existence, if we can call it that. The constant movement, but without purpose or destination. The grain doesn't need to go anywhere. It simply exists, responding to the physical forces acting upon it. Water moves it one way, wind moves it another. Gravity pulls it down the beach face. Waves push it back up. The grain is part of a larger system. The beach as a whole, which is itself part of the coastal system, which is part of the ocean system, which is part of Earth's water cycle. Energy from the sun drives the winds that create waves. The gravitational pull of the moon creates tides. Rivers bring new sediment to the coast. Tectonic forces slowly raise or lower the land. All of this is happening, has been happening for millions of years, will continue happening for millions of years to come. Our grain is just one small part of it, but it has been part of these processes for a very long time now. Beaches are windy places. Wind is created by differences in air pressure, which are ultimately caused by the uneven heating of Earth's surface by the sun. The ocean and the land heat up at different rates, creating pressure differences, and therefore wind that blows onshore during the day and offshore at night. When wind blows across a beach, it can pick up sand grains and carry them, not large grains. Wind isn't strong enough to move pebbles or coarse sand, but fine sand, grains about 1/4 of a millimeter in diameter, can be lifted by moderate winds. Our grain is near the upper end of what wind can move. It is perhaps 1/2 millimeter in diameter now, after all the abrasion it is experienced. A strong wind might be able to pick it up, but a light breeze won't. One day, a storm is approaching from offshore. The wind picks up, blowing steadily from the ocean toward the land. The wind speed increases to perhaps 30 or 40 kilometers per hour. A strong breeze, but not yet a gale. This is enough. The wind picks up our grain, along with thousands of others, and carries them up the beach. The grains don't fly high. They travel in a layer just a few centimeters above the sand surface, bouncing and hopping along. This motion is called saltation, a word that comes from the Latin word for jumping. Each grain makes small hops. It is lifted by the wind, travels forward a short distance through the air, then falls back to the surface where it bounces and is lifted again. The grain might travel 10 or 20 centimeters with each hop. The wind carries the grain across the beach, past the high tide line, into the area of older, drier sand behind the beach. Here, there are small dunes, mounds of sand held in place by sparse vegetation. Beach grass, maybe some low shrubs that can tolerate the salt spray. The wind slows when it encounters these obstacles. The vegetation disrupts the airflow, creating eddies and reducing wind speed. When the wind slows, it can't carry the sand grains anymore. They fall out of the air and settle on the ground. Our grain lands in the lee of a clump of beach grass, on the side away from the wind. Other grains are landing here too. Over the course of the storm, which lasts for a day or two, thousands of grains accumulate in this spot. This is how dunes grow. Sand is carried by wind from the beach and deposited in areas where something, vegetation, rocks, driftwood, disrupts the wind flow. Over time, the accumulation of sand creates a mound. The mound itself then becomes an obstacle that disrupts wind flow and causes more sand to be deposited. Our grain is now part of a dune. It is buried under a few centimeters of other sand grains. The beach grass grows up through the sand, its roots holding the grains in place, stabilizing the dune. Dunes are different from beaches. They're more stable. For one thing, the sand isn't being moved by waves every day. It only moves when the wind is strong enough, and even then, it doesn't move far. The grass roots create a network that holds the sand in place. It is also drier here. Rain soaks into the sand quickly, draining down toward the water table below. Between rain events, the sand is dry, loose. If you were to run your fingers through it, it would flow like a very slow liquid. The grain sits in the dune for years, decades perhaps. More sand accumulates on top of it. The dune grows larger, the beach grass grows thicker, more established. The roots extend deeper into the sand, but dunes are not completely stable. They move over time, in a process that is visible if you watch for decades but invisible in the short term. Wind erodes sand from the windward side of the dune, the side facing the prevailing wind, and deposits it on the leeward side. Gradually the entire dune migrates in the direction of the wind. It is a slow process. A dune might move a few meters per year, but over centuries, a dune can travel a significant distance, slowly walking across the landscape. Our grain, buried in the dune, participates in this migration. Every few years, wind might expose the grain on the windward side and carry it over the top of the dune to the leeward side, where it is buried again. Slowly, very slowly, the grain moves inland, away from the beach. The environment changes as the grain moves farther from the shore. The sound of waves becomes fainter. The salt spray doesn't reach this far inland. Different plants grow here, not just beach grass, but other species that can tolerate sandy soil. Some coastal dune systems are quite extensive, extending kilometers inland from the beach. These are called dune fields. The sand is older here, sometimes thousands of years old. Some of these grains haven't seen the ocean in a very long time. Our grain might stay in this dune system for centuries, or it might be excavated by wind during a particularly severe storm and carried back toward the beach. Dunes are dynamic systems. Sand moves in and out of them continuously, just slowly. For now, though, the grain is stable. It is buried about 20 centimeters deep in the dune, surrounded by other grains, roots growing through the space between grains. It is dark here and quiet. The only sound, if there is sound, is the faint whisper of wind across the surface of the dune above. Let's pause again and think about time. Our grain has been on its journey for a very long time now, hundreds of thousands of years. Perhaps 250,000 years since it broke free from the granite in the mountain. This is difficult for us to truly comprehend. Human lifespans are measured in decades. A long human life might be 90 or 100 years. The grain has been traveling for 2,500 human lifetimes. Civilizations rise and fall in less time than this grain has been moving. The Egyptian pyramids are about 4,500 years old, ancient by human standards, but the grain had already been travelling for tens of thousands of years before the first pyramid was built. Agriculture, the invention that allowed human civilization to develop, is only about 10 to 12,000 years old. Our grain was already on a beach, being moved by waves before humans learned to plant crops and domesticate animals. And yet, from a geological perspective, the grain's journey is not particularly long. The mountain where the grain came from might be 50 million years old. The oldest rocks on Earth are over 4 billion years old. Our grain's 250,000 year journey is just a moment in geological time. This is one of the strange things about thinking about deep time. Human time and geological time operate on such different scales that they're almost incomprehensible to each other. Things that seem permanent to us, mountains, coastlines, are temporary and changing from a geological perspective, and things that seem impossibly slow from our perspective, the movement of continents, the rise of mountain ranges, are the fundamental processes that shape our planet. The grain doesn't experience time, of course. It is not conscious. It doesn't remember where it has been or anticipate where it is going. It simply exists, moment by moment, responding to whatever forces act upon it. But there is something profound about that existence, isn't there? The grain has been present through ages of Earth history that humans never witnessed. It was tumbling in a river during the Ice Age, when mammoths and saber-toothed cats roamed the continents and ice sheets covered much of the northern hemisphere. It was on a beach when the ice melted and sea levels rose, flooding coastal areas and creating the modern coastline. The grain is a time traveller, in a sense. It carries its history with it, encoded in its shape, its size, its surface features. A geologist studying the grain under a microscope could make educated guesses about where it came from, what kind of environments it passed through, how long it has been travelling. The rounded shape tells us it has been in transport for a long time, tumbled by water and wind until all the sharp edges were worn smooth. The size, medium sand, now after all the abrasion, tells us it has been travelling long enough to be substantially reduced from its original size. The fact that it is quartz tells us it came from igneous or metamorphic rock originally. Quartz is one of the most common minerals in Earth's continental crust, and it is highly resistant to chemical weathering. That is why quartz makes up such a large percentage of beach sand. It outlasts other minerals. If we could examine the grain at an atomic level, we would see tiny imperfections in the crystal structure. These imperfections, called defects, are created when the grain is subjected to stress, or when radiation from radioactive elements in surrounding rocks disrupts the orderly arrangement of atoms. These defects accumulate over time, and scientists can use them to estimate how long the grain has been exposed to radiation, which gives an estimate of how long it has been at or near Earth's surface. But the grain doesn't know any of this. It simply is. It exists in the present moment, buried in a dune surrounded by other grains. The past is gone. The future hasn't happened yet. There is only now. This is perhaps something we can learn from the grain, not that we should be passive or without purpose. We're not geological objects, after all. We're living beings with consciousness and choice and responsibility. But there is value in remembering that we too are part of deep time. The atoms in our bodies were formed in stars billions of years ago. The oxygen we breathe was produced by photosynthetic organisms over millions of years. The ground we walk on is made of rock and sediment that has been through countless cycles of formation and erosion. We're temporary, just like the grain is temporary. Eventually, the grain will be worn down to nothing. Or rather, it will be broken into smaller and smaller fragments, eventually dissolved into solution, eventually perhaps incorporated into new rocks or taken up by living organisms. We're temporary too, our lives brief compared to the age of the Earth. But we're part of something larger, something that has been going on for billions of years and will continue for billions more. There is something peaceful in that thought, isn't there? We don't have to carry the weight of permanence. We can simply be for a while part of the ongoing story of Earth and matter and energy. Like the grain, resting in its dune, part of the landscape, part of the cycle, waiting for the next wind, the next wave, the next movement in a journey that has no final destination. Time continues to pass. The grain rests in the dune for perhaps 200 years. The dune grows larger, more stable, the vegetation becomes more diverse. What was once a small mound of sand near the beach is now a substantial dune ridge, several meters high, with mature beach grass and shrubs. But nothing lasts forever. Climate changes over time, precipitation patterns shift. A period of drought comes to the coastal region where our grain rests. The drought lasts for years, then decades. The vegetation that stabilized the dune begins to die back. Roots no longer hold the sand in place. At the same time, storm patterns change. More frequent and more severe storms reach the coast. These storms bring strong winds that erode the dune. Sand that was stable for decades is now exposed to wind and carried away. Our grain, which had been buried deep in the dune, is slowly uncovered as the dune erodes from above. First, the 20 centimeters of sand on top of it is blown away. Then the grain itself is exposed on the surface. A strong wind comes during a coastal storm. The wind picks up the grain and carries it, saltating across the eroding dune surface. The grain travels maybe 100 meters in a few hours, blown by the wind, until it reaches the edge of the dune where the sand meets the beach. Here, the wind slows, disrupted by the change in surface texture. The grain falls out of the air and lands on the upper beach, above the high tide line. It sits there for a while, a few days perhaps. Then a particularly high tide, combined with storm surge from the approaching storm, brings waves up onto the upper beach. A wave washes over the grain, picks it up, and carries it back into the ocean. The grain is back in the surf zone, tumbling in the turbulent water where waves break on the beach. It collides with countless other grains rolling and bouncing along the sandy bottom. This environment is familiar, in a way. The grain was here before, perhaps 200 years ago, before it was blown into the dune. The grain has returned to the ocean, the place where it spent 25,000 years buried on the ocean floor in an earlier part of its journey. The waves move the grain back and forth across the beach face. Sometimes the grain is carried up the beach by an incoming wave. Sometimes it is dragged back down by the backwash. The net movement over time is difficult to predict. It depends on the wave characteristics, the tide, the season, the weather patterns. During calm weather, waves tend to push sand up onto the beach, building the beach higher and wider. During storms, waves tend to erode the beach and carry sand offshore. Our grain participates in this back and forth movement. A large storm arrives, perhaps a hurricane, bringing powerful winds and enormous waves. The waves are several meters high, crashing onto the beach with tremendous force. The grain is picked up by these waves and carried offshore, tumbling violently in the turbulent water. The grain is carried farther offshore than it has been in a long time. It is deposited in about 15 meters of water below the normal wave base, the depth where waves can no longer move sediment during ordinary conditions. Here, the grain settles into the sediment. The water above is calmer, though the surface far above is still being churned by the storm. The grain comes to rest among other sand grains, silt, and fragments of shell. This could be the beginning of another long period of rest on the ocean floor, like the 25,000 years the grain spent there before. But geological processes work on multiple timescales. Something that might take tens of thousands of years in one situation might happen much faster in another. In this case, the coast where our grain now rests is actually rising. This is happening because of post-glacial rebound. The land is slowly rising because the weight of the ice sheets from the last ice age has been removed. The ice melted, and the land, which had been pressed down by the weight of the ice, is now slowly springing back up. This process is gradual. The land might rise a few millimeters per year, but over centuries it adds up. The water that is now 15 meters deep will eventually be shallower as the land rises. Also, sea level is changing. Over the past 10,000 years since the last ice age ended, sea level has generally been rising as ice sheets melted. But sea level doesn't rise uniformly everywhere, and it doesn't rise steadily. There are variations based on ocean currents, local geological processes, and other factors. In this particular time, sea level is relatively stable. The rising land means that the water is gradually becoming shallower, even if sea level itself isn't falling. Over the next few thousand years, the depth above our grain decreases. What was 15 meters becomes 12, then 10, then 8. The grain is gradually entering shallower water, back into the zone where waves can occasionally disturb the bottom. A storm comes, and the waves reach down to the bottom where our grain rests. The grain is picked up and moved shoreward. Then another storm, years later, moves it farther, eventually, and we're talking about a process that takes several thousand years. The grain is back in the surf zone, being tumbled by waves that break on the beach. The grain is on a beach again. Perhaps it is the same beach where it was before, or perhaps the coastline has shifted and it is a different beach. Coastlines change over thousands of years. Rivers change course. Sediment is deposited in new locations. Erosion removes sediment from other locations. The grain doesn't distinguish between one beach and another. They are all the same from the perspective of a grain of sand. Places where water and air meet, where waves move sediment, where the grain is tumbled and sorted by size and density. The grain has been on its journey for hundreds of thousands of years now. It is smaller than when it started, perhaps a quarter or a third of its original size. All that tumbling, all those collisions have worn it down slowly, but inexorably. The grain is now fine sand, at the smaller end of the sand size range. It is about 1/4 of a millimetre in diameter, perfectly rounded, smooth and polished by its long journey. It is still quartz, still the same mineral that crystallized from magma deep in the earth millions of years ago, that was lifted to the surface as part of a mountain range, that broke free from granite and began its journey. How much longer will the grain's journey continue? That depends on many factors. Quartz is durable, but not indestructible. Eventually, the grain will be worn down so small that it is no longer sand but silt. Particles smaller than 0.0625 millimeters in diameter. As silt, the grain will behave differently. It will be carried farther by water and wind because it is lighter. It might be carried far out to sea in suspension, staying in the water column for a long time before finally settling in deep ocean sediments. Or the grain might dissolve. Quartz is not very soluble in water, but it does dissolve very slowly, especially in water that is slightly alkaline or that contains certain ions. Over very long periods of time, the grain could be dissolved into solution, the silicon and oxygen atoms separated and carried away in the water. Those atoms might eventually precipitate out again as new quartz crystals in sedimentary rock, or they might be taken up by living organisms, diatoms for example, tiny marine organisms that build their cell walls from silica. When the diatoms die, their silica skeletons fall to the ocean floor and accumulate as sediment, or the grain might end up in sedimentary rock. If it is buried deeply enough and subjected to enough pressure, the surrounding grains might be cemented together by minerals, precipitating from groundwater. The grain would become part of sandstone. If that sandstone is then buried even deeper and heated, it might metamorphose into quartzite, a metamorphic rock where the quartz grains are fused together into a solid mass. And if the quartzite is buried deeply enough and heated to melting, it could become part of magma again, the quartz dissolving into the molten rock. The cycle would come full circle. The grain that started as a crystal in granite could end up as part of granite again, or some other igneous rock, waiting to be lifted to the surface by tectonic processes and weathered and eroded and transported all over again. This is the rock cycle. The continuous transformation of rock from one form to another, driven by tectonic forces, weathering, erosion, deposition, and metamorphism. The cycle has been operating for billions of years, long before there was life on Earth, and it will continue for billions of years into the future. Our grain is just one small part of this cycle. It has been through a few steps: crystallization in magma, weathering out of granite, transport by water and wind, deposition in various environments. It might go through more steps, or its journey might end in deep ocean sediments, buried so deeply it never returns to the surface. We can know for certain. The grain's future, like all futures, is uncertain. It depends on conditions we can predict, where the next storm will take it, how much longer it will remain sand before being worn down to silt, whether it will be buried in sediments or remain at the surface. But the uncertainty doesn't matter, really. The grain doesn't worry about its future. It simply exists, moment by moment, responding to whatever forces act upon it. And there is a kind of peace in that existence, isn't there? No anxiety about what comes next. No regret about what is past. Just being here and now, a grain of sand on a beach. Part of the earth, part of the ongoing transformation of matter. We followed one grain of sand on its journey from mountain to ocean, through rivers and deltas and beaches and dunes. We've seen how slow geological processes, weathering, erosion, transport, deposition, can transform rock into sediment and move that sediment across continents and into oceans. We've thought about time, the vast stretches of deep time that govern geological processes, so different from the brief spans of human time. We've considered what it might mean to exist without purpose or destination, simply being present and responding to the world. These are big thoughts, perhaps too big for bedtime. But there is also something calming about them. The grain's journey reminds us that the world is old and will continue long after we're gone. Our anxieties and worries, our deadlines and obligations are real and important in our lives, but they're also temporary, brief moments in a much larger story. The grain doesn't worry, it simply is. And maybe, as we drift off to sleep, we can let go of our worries for a while and simply be as well. The grain is still out there somewhere, on a beach or in a dune or buried in sediment. It is still being moved by waves or wind, still slowly being worn down, still on its journey. That journey has been going on for hundreds of thousands of years, and it will continue long after we've fallen asleep, long after we wake up, long after we've forgotten about this particular grain of sand. And that is okay. The grain doesn't need us to watch over it. It doesn't need our attention or our concern. It will continue on its way, patient and persistent, shaped by forces much larger than itself. Maybe we can be like that too, in our own way, patient, persistent. Trusting that we're part of something larger, part of cycles and processes that have been operating for a very long time and will continue operating regardless of our individual worries. The beach is quiet tonight. Waves are washing up on the shore, gentle in the calm evening air. Each wave brings millions of sand grains up the beach and carries them back down. The grains tumble over each other, smooth and rounded, polished by their journeys. Our grain is among them, indistinguishable from the others. One small part of the beach, one small part of the Earth's crust, one small part of the story of our planet. And the story continues. The waves keep washing up the shore. The wind keeps blowing. The rivers keep carrying sediment to the sea. The mountains keep slowly eroding. The ocean floor keeps slowly accumulating sediment. All of it moving at its own pace, in its own time, part of the patient, persistent work of the Earth transforming itself, moment by moment, year by year, millennium by millennium. Rest now, the grain's journey continues, but you don't need to follow it any longer. The waves will keep moving the sand, the story will keep unfolding, everything will continue, as it should. Sleep well.